Since states of matter is going to be important, I want us to list out, before we even dive into the types of reactions, your signs of a chemical reaction. So kind of write that in a little square off to the right, maybe. Signs of chemical reaction. So this is like what you're actually looking for in the lab, okay? So, what are a couple that you guys remember?
Burning.
Formation of bubbles or gas.
Let's do that one. So, formation of gas, so possibly bubbles. Hold on. And also odor sometimes. Although we also found out, though, you got to be careful with the odor one, because sometimes you're breaking intermolecular forces, not changing your substance. So you got to really be careful with using odor as your only way to know that a gas was formed, right? And so, so I know you said burning. So let's talk about him saying burning real quick, because I don't want to totally ignore that. What are things that you see or you sense?
Ash. I said ash.
So what would tell you about that ash that makes it a
Carbon.
chemical change? No.
Just remove the carbon.
I think someone over here had said it. Okay, we can do that one. That's for burning, right? So we can do change in temperature. Can get cold or can get hot. What's something you see, though?
Light. Oh, yeah. I said
Light.
color.
So see light. And then what did you say? Oh, you said light too. Color. That's what I was going for with the ashes. You see a color change, right?
Wait, but can't that be like light too?
Yeah. But this would be like if I'm mixing some liquids together or something. Okay. Color change. And there's one more big one. Sometimes we mix a bunch of liquids together. Yes, a precipitate forms. And we're going to go into detail in that today. Okay? So a precipitate forms. And what state of matter is a precipitate? What makes it so distinct? It's a solid. Good. And remember, it's very specific to... I put two liquids together and now a solid forms. Okay, it's not just something didn't dissolve or something, okay? All right, all good? So those are your signs of a chemical reaction or signs of a chemical change, okay? Let me put a little box around that. All right. So when we go to approach these labs, you really want to focus on when you see those, and that way you can figure out what was actually going on. All right? Now, your types of reactions. Okay, so we have our synthesis. Okay, and if you remember, this is the one where they just get together, right? So we have, what we wrote as like the skeleton of what they look like is A plus B makes AB. So combination, they combine. Okay? And sometimes you'll see it called combination on other worksheets, so just so you know, same thing, synthesis. Okay? So a couple hints though for these. For your products, you want to make sure you crisscross charges if ionic. Right? So that's where you take your positive this, negative that, crisscross them to make your subscripts. So when you're forming the product, you're making sure you're respecting the fact that they have to combine in a certain ratio as ionic substances. Okay? If you're trying to figure out your reactants, you need to be remembering your diatomics. Those show up a lot. So I know you already have them written on that other page, but if you want to get it in your journal, remember that you start at the number 7 on your periodic table, which is nitrogen, all the way to fluorine, all the way down to iodine, and then hydrogen. So you start at the 7, you make a 7, and then there should be 7 of them. Lots of 7s. It's your diatomic 7. Okay? Start at the 7, make a 7, hydrogen makes it a total of 7. Okay? And remember what this means is you put a little 2 next to these guys. They have to exist with another one. Okay? It's only if they're by themselves. Don't worry about it for crisscrossing charges. The charges still get crisscrossed as is. Okay? We good so far? Okay, so let's talk about the one that's pretty identical to it. I really messed this up. I'm gonna scooch these guys all the way off to the side. Okay. There you go. All right. So, let's talk about the one that is decomposition. Position, sorry. Reaction, yes. Yep. And this one was the one where you had A, B, but they break apart. So the breakup. Okay? So, if you look at these 2 skeletons, they look pretty similar. Do you see that? For synthesis versus decomposition? Okay? Yeah, they're both backwards flipped. Maybe? I don't know. All right? So, all that we're going to write here is C synthesis. Okay? So if you want to know the reactants, you're basically going to make sure you're crisscrossing charges from what was formed in the products. And then when you're making your products, you want to make sure you're including your diatomics. So you're kind of using the same rules, just make sure you kind of either crisscrossing or diatomics. That's really all you got to know. Yeah. What? Okay. All right. So are we all good there? Okay, because I'm going to switch screens. We good? Okay. All right. Next, we have single replacement. So remember that one was steal your girl or boy or whatever. You're stealing somebody. Okay, so single replacement. So I need you guys to now start focusing on the 2 different types of single replacements. Okay, so there is a cationic that one would look like A plus BC. He would kick out the first one listed. So it is a cation replacing a cation. Okay? So then we would leave B on its own plus AC. And again, for all of these, when you're forming new compounds, crisscross charges, and make sure you're including any diatomics that need to be respected. Okay? So don't forget your diatomics and I'll just write that. Diatomics and crisscross. So don't forget that hint. The other thing to notice is for your cationic, that's usually dealing with metals by themselves or hydrogen, because these guys have the positive charges usually. So hydrogen happens to fall in column 1 or group 1 on the periodic table. He's a plus charge. He usually gets booted out. We're going to talk about that in a second. Okay?
Wait, so does this happen like naturally?
Yes.
Or is there like...
I'll show you. I'll show you what you can look at, and then you'll see which ones happen naturally. Yep. All right. The other kind of single replacement is an anionic. I am am misspelling things left and right, so please feel free to tell me if I spell something wrong. All right, so anionic. An anionic thing would be A plus BC, but A kicks out C instead. So C is left alone, and now you have BA.
It's like the same thing.
Same thing, except now we're kicking out the anion, which is usually the second thing listed, right? So this is usually your non-metals that you're looking for. So A would be a non-metal, and up here on cationic, A would be a metal. It's an easy way to kind of notice it, okay? Now, so with your single replacement reactions, in order to come up with what your products are or whether that reaction is even going to happen, you guys are going to be referring to your periodic table, okay? So draw an arrow down from cationic, and you're going to say, use your activity series. Bless you.
Bless you.
Inside the periodic table. Okay? We'll add something to it in just a second. So what I'm going to have you guys do is take a look at your periodic table, open it up to the inside, and I will put up here what you guys are looking at. Okay, so you guys are looking at the inside of your periodic table, yes? All right, so take a look at your activity series. Just kind of skim through this little list. Look at what you see, look at what you notice. First thing that should stand out to you is what are most of these things? Metals, right? Except for there's one in parentheses, and hydrogen, okay? But these are all cationic things. So for your cationic single replacement, you're going to be referring to your activity series. Now, just like if you're trying to replace somebody's boyfriend or girlfriend, you got to be better than the person that you're replacing. If you're not, then that other person probably needs to check their life out a little bit. But they probably shouldn't be choosing you. All right. But if you're better, that's what it is, right? So so you have to be better than whoever you're trying to replace. So same thing, when you're looking at this activity series, if it is at the top of the list, it can bump out anybody at the bottom of the list, anybody below it. All right? So who's bumping out everybody? Lithium. Who is probably going to get replaced no matter what? Gold. All right? So, yes, feel sorry for gold. It's okay. They'll find their way. All right. That's why he has alloys. All right. So, so you see that a lot of the, and something to kind of notice, my AP kids and I were talking about this, was silver, platinum, and gold. Those are usually our jewelry, right? And even copper. So all of those things, those are at the bottom of this. So meaning they don't really, they're not going to react with things like most of our acids. Okay, acids tend to have hydrogen. So if you notice, hydrogen is above all of these guys. So if I accidentally dropped my ring in there, minus the fact that it is an alloy, so there's other stuff in there, but if I dropped pure gold in there, it wouldn't get damaged. Like those are kind of things to think about. That's why maybe we pick those types of materials. Okay.
Doesn't copper react no matter what to oxygen though? Because then it becomes like.
You're talking about just something else. That's a chemical reaction. So yeah. All right. All right. So so with this, anything at the top can bump out anything below it. All right, so that's all that we're going to add to our little notes right here. I'm going to push that off to the side. We're going to say a metal can replace anything below it. Okay, I have to keep including hydrogen. It can bump out hydrogen. That's the most typical reaction that we see, is we're going to bump out the hydrogen in acid and to make your hydrogen gas or bubbles, okay? And that's one that you guys have had to write a couple times. If I drop a solid magnesium into hydrochloric acid, you get hydrogen gas. Okay?
Or if you drop sodium into water.
You get hydrogen gas. Good job. Yep.
Yeah.
You get hydrogen gas, which is highly flammable. So that's why you get the fire.
Like when I go to when I throw it into like a lake.
That one's a little different. He's not listening. All right. All right. So another thing that I do want you to add to these notes is that differences in their activity. So what do you guys think I mean by their activity? Do you see that big arrow?
Electronegativity.
No. Do you see that arrow next to your list? Yeah, you have the arrow going up, right? So the differences in their activity, meaning something like lithium and potassium, they don't have a very big difference. But lithium and lead, big difference. Do you see that?
Yes.
Okay, so when we have a bigger difference, it usually means that the reaction's also going to go a little bit faster. You're going to see it happen a little bit quicker. It's going to bump it out right away. Versus something that's right there and it has about the same activity as the other one, you're going to have to wait a little bit. And you'll see one, a specific station that you guys are going to do on the next lab, you'll see one that takes forever because they're so close together on this activity list. So differences in activity determine speed. Of reaction. And that's not the only thing that determines speed of reaction. That's a whole other unit. Okay? But that's something to kind of make note of in your lab when you go check that out. Okay? All right. So we made an arrow from cationic stuff, but what about the anionic stuff, right? And so so for anionic, you are going to, I'm so sorry, I'm running out of room. So for the anionic stuff, draw another arrow. Okay? You're going to use your halogen list. On your periodic table. Okay? So the halogens are group what? Group 17. Not noble gases, the one next to the noble gases, right? And so that's just your fluorine, chlorine, bromine, and iodine. Those are typically the ones that we're going to see in the single replacements that are anionic. If you happen to come across another thing, do your research, use Google. Most of y'all have it on your little phones, or you can use my computer in the back, okay? And it's okay to do research because honestly, chemistry, you learn as you're doing it. It's not something that we can just give you everything about chemistry and you know it and you'll be experts walking out of here this year. No. Some of it you got to learn as you're kind of going along and you'll see some stuff. It comes from experiences. So so if anything doesn't fall in these rules, just look it up. Okay? All right. AP kids do it all the time. So anyway, according to this little list, okay, who's going to bump out pretty much everybody? Fluorine, exactly. And iodine will always get kicked out. Okay? So we got that? Okay, so that's how you're going to use that for anionic. Any questions on single replacement? Okay? All right, so next one we're going to talk about is double replacement. And I will finish this up kind of quickly. I'll try and be quick. But for double replacement, we do have a little bit to write on it, okay? Because there is another chart that you're going to be referring to, so keep your periodic table out right in front of you.
So is this going to be like a lot? Because I have like
You might go on the next page. Okay. I would say you need about half a page, y'all.
Oh, okay.
Sorry, or write sideways.
Okay.
One or the other. Okay. So you can write on the back if you guys need to. All right, so double replacement. So if you remember, this was the one that we called double date gone wrong. Some of y'all like to call it gone right. Okay, but you have the couple show up to the date, and then they decide that they're going to date the other person. Okay, so A and C switch. Okay, so one thing that I want you to note on this, because biggest mistake is people switch more than two of the letters and then they put them in the wrong spot. A first thing listed has to replace another first thing listed. Cations replace cations. If you choose to replace the second, guys, anion has to replace an anion. Do not put two cations together. Don't switch your anion and cation. Okay, I would just keep it simple and take the first two things listed and switch them spots. Okay, that's it. All right, so then you would end with CB, so if you notice, C is still listed first, plus AD. Okay? All right, so important thing on this would be definitely remembering to crisscross charges. Okay? The next important thing is knowing what the heck you're supposed to put for your states of matter. So remember, when in doubt, you're going to put aqueous, but I'm going to give you a way to know when it's not going to be aqueous. Okay? Okay, so aqueous is usual, so we can put aqueous as the typical. But technically, if everything ends up aqueous, if it all started aqueous and it all ends up aqueous, you really didn't have a reaction. You didn't see anything cool happen. What is going to tell us that a reaction happened? If I have two liquids, I mix them together, what's going to give it away? Solid or gas, okay? So solid and gas is going to be the way that you know a double replacement actually happened, okay? All right, so, all right, so you're going to look at your periodic table again on the inside, okay? I want you to look at the center of it. All right, so back on the center, we're going to look at that center part. Okay, so you see there's solubility of common ionic compounds in water. Okay, now when we say in water, that means in solution, right? So all of our stuff usually in your chemistry labs, we're making you solutions. I give you a 0.5 molar solution or whatever. And that's just talking about how many of the particles I dissolved in the water to begin with. So all of it has to do with being dissolvable in water, okay? And so the way that you're going to use this chart is you have all these little compounds. If you notice, they're all half of some compound. Do you see that? So you have your acetate up at the top, you have your ammonium, nitrate. Those are all polyatomics, things that you can find on that left-hand side on your list of polyatomic ions. So if you have these ions in a compound, they're soluble. The top chart is telling you they are soluble unless you have your common exceptions, and then you have lists sometimes, okay? So if you notice all these guys at the top, do they have any exceptions? No, so we're going to go ahead and say they're always, always, always soluble. And that's kind of a way to start speeding through these a little bit. For now, make sure you're just using this chart all the time. But that's going to be something, especially those of you who are planning on doing AP chemistry, polyatomics are one of the things that students are expected to know walking in. Memorize them, or at least most of them. I'm speaking for my AP students. Yeah, you can learn some of them in the first week, but they also come in knowing all their solubility rules. So walking in knowing, oh, that one's going to form a solid, that one's going to be aqueous. And there's an easy way to learn them. I will post an extra video if it's something that you're interested in. It's called NAGSAG, and it's a way that you can actually memorize them like that. It's very quick, it's very easy. I'm not going to take class time to teach you guys it, okay? But if you want to come talk to me, you can talk to me or watch that video. It's like 3 minutes. All right, so we're going to be using these solubility rules. So you guys saw the word soluble, and then if you looked at the bottom of the chart, it says insoluble, right? So now you're going to use that bottom part opposite of how you use the top part. These guys are not soluble unless, and then you have that list of exceptions right there, okay? And by the way, who are your alkali metals?
The ones
Group 1. Anytime you see anything listed in group 1, if you notice, those are always exceptions. So those guys are always soluble, okay? It's an easy way to kind of start getting used to them. That's a memorization tool right there. All right, so let's talk about what soluble and insoluble mean real quick. They are words that we've seen before, but just in case. We got soluble, which means they're able to dissolve. Or aqueous, okay? So state of matter, aqueous. Insoluble is opposite. So not able to dissolve. Or solid. Okay? So this would be the precipitate. Okay? Or it would be something that if I had it in the storage room, if I have that solid and I go to try to mix it in water to make you guys a solution, I'm going to have to add something to make sure it goes into solution. It's not one that just does it. Okay? So, and usually we're not trying to make solutions with them. We leave them solid. Okay? All right. So, soluble and insoluble. So when you are using your little chart right there, just know that you're kind of telling yourself the following sentence. So for the top part, you're saying blank is aqueous unless, and then you're reading the exception. And if you just literally tell yourself that sentence every single time, you won't mess it up. Some people feel dorky saying that sentence, and then they don't do it, and then they mess up. So just get over it. We're all in the same challenge right now. So say the sentence to yourself. It helps. It literally helps. All right? The bottom part of the chart where it's talking about insoluble, okay, you're saying blank is solid unless, and then you say your little exception. Okay? Okay. So, I'll leave that right there. So once again, I will post the video. What you'll see if you watch the video to help you with it is it'll look like this, NAGSAG. And all that it's going to stand for is nitrates, acetate, group 1, and then this will be sulfates, ammonium, and group 17. And then with that, it'll give you the two exceptions, the two major exceptions, which is going to they're called the PMS rule and the Castro-Bear rule. And then what that does is this right here, all of that listed right there, is your entire solubility chart. And you kind of start noticing the same exceptions in the same categories, okay? So if you're interested, go watch that, and I can give you a couple extra things that we also do in AP if that's something you're interested in, okay? It is a time saver. It helps you not have to look at the chart. So just heads up. All right, so the part that I do want you to add, though, to your notes, down here, put a special double replacement. Does anybody remember which one is the special double replacement? Huh? Any ideas? Not really? Thank you for being honest. Okay. Neutralization. Okay. So neutralization is always going to have an acid and a base, and you're neutralizing it to salt water. Okay. So you have your acid and base, so we're going to show it. This is how you write acids. You write Ha. Okay, so what you're showing is an H in front of some compound. That's your acid. Plus your base, followed up with usually a hydroxide. Not all the time. So I don't want you to think these are always what they're going to look like on the reactant side. But you guys haven't learned acids and bases yet, so I think it's harder for you guys to recognize an acid-base thing with just that part. It's going to be challenging until you learn it. So what you guys should really focus on is going to be making that salt water part. So you are looking for water, which remember, how did I tell you guys to always write it? HOH. And that shows you that double replacement happening. The H and the OH come together to make water. And then you're making some sort of we're going to put Ba, which is your ionic salt. Okay, so remember it's not always NaCl. It's just an ionic substance. So metal and a non-metal. Okay, and make sure you crisscross charges. Don't forget. All right, you guys have a tiny bit of extra time than first period did, so I'm going to add in combustion, and then you were done. Okay, and these are pretty much the notes that you're going to be using for this chapter. And we're pretty done with it, minus all the balancing stuff. So make sure, if you never became comfortable with balancing, you're coming in for tutoring to see me so I can get you caught up. Because we have to keep moving forward. We're a little behind, especially with Miss Vogel being out for those couple days. Okay? All right, so the last one we're going to write, Jen.
Can you go back, please?
Can we go back in a second? Oh. Because I was going to say, write this down real quick. Okay. All right, so combustion. Remember, we're putting CXHYOZ, and sometimes you'll see nitrogen to pop up in there, okay? But those are the three main components of your hydrocarbon, which is your fuel. Okay? You always have some sort of a fuel reacting with oxygen, which feeds fire. Okay? This is the basic combustion. There are other ones. Okay? To make, what are always going to be the products?
Ash.
Carbon dioxide and water. Always, always, always. So you are looking for these ingredients going this way. So if I only give you this part, you fill in this part. Okay, so if you see a hydrocarbon with some oxygen, most likely it's combusting. Put carbon dioxide and water, you're done. Okay? If you see, I will never most likely give you just that part and tell you to find this part until we get to empirical formulas. Then there's like a little challenge problem it's fun. I say it's fun. I don't know if y'all like it, but it's fun. And that's a whole different thing. And you find out what that actual compound is. There's a way to do it. So those are your types of reactions. Make sure you know it. On the combustion, add that little triangle right there. You do need usually some sort of a spark to get it to go. Okay? Other than that, I will get you guys started on the page that I showed you at the very beginning. And so you guys are going to be doing, for homework tonight, all the types of reactions for it. Okay, so you're just going to go down your list and find all the types of reactions.